Hi once again, folks. This is the final lecture in the Series 5 that has to do with the Laplace Transform. And the topic of this lecture is essentially the relationship between circuit analysis and the Laplace Transform itself. Okay, the motivator for all of this is the fact that reactive circuit elements exhibit differential relationships between current and voltage. We represent these relationships directly when we compute impedance for circuit analysis. Okay, the first circuit element is the capacitor, and the differential relationship between current and voltage, as you know, is I of t equals C dV of t dt. And so what that says is that the current through the capacitor is proportional to the derivative of the voltage across the capacitor. And that constant of proportionality is the capacitance itself. Now, what if we take the Laplace transform of that expression? Right? So we want to take the Laplace transform, and what we're going to get is I of S, that's the Laplace transform of the current, equals C times the Laplace transform of dV dt. Okay, and we got to work on what that is, but we can say, well, we know that's going to be C times S V of S minus V of 0 minus, so the initial condition value. All right, so I can write that all together on one line as I of S equals S C V of S minus C times V of 0 minus. Remember, this is just a scalar value. If I solve for voltage, then I can say V of S is 1 over SC times I of S, and in this case I'll have plus V of 0 minus over S. Okay, so algebraically when you work it out, you're going to have that S in the denominator there. Now it turns out this 1 over SC, right, if we replace S with j omega, that's 1 over j omega C, so that is our impedance Z of C that we've worked with many, many times. Okay, for the inductor, the differential relationship is V of t equals L di of t dt, right? So that says that the inductor voltage is proportional to the derivative of the current. And again, the proportionality constant is the inductance. If we do the Laplace transform, we're going to have something that looks like, and I'll just directly write it here, is V of S, the Laplace transform of the inductor voltage, equals L times S times I of S minus I of 0 minus. Okay, so if we distribute, we're going to have SL onto I of S minus L onto I of 0 minus. Okay, this SL is going to be our inductor impedance, right? Because that would be j omega L if we substitute. And for completeness, we can also solve for current. And so we'll have the Laplace transform of the current is going to be 1 over SL onto V of S plus I of 0 minus, again, divided by S. There isn't much excitement about resistance because it doesn't have a reactive nature, so there's no differential relationship between voltage and current, right? It's just a constant of proportionality between current and voltage itself. Okay, so the major takeaway of this, which was introduced in the beginning of this series, is that the Laplace transform can be used to effectively analyze linear circuits. Specifically, the major benefits are that it can handle non-zero initial conditions, it can handle transients, and waveforms other than sinusoids. So essentially, it's a unified toolbox that allows us to do a broader range or class of circuit analysis than possible with simple phasor analysis. So to dig into this discussion, let's recall the simple RC low-pass filter that we've looked at a number of times. It's a good candidate circuit that can be used to make these points without overwhelming us with the complexity. Okay, the differential equation is V out dot plus 1 over RC times V out equals 1 over RC times Vn of t. All right, so that's a nice, simple first order linear ordinary differential equation with constant coefficients. Okay, so we're going to look at our analysis by taking the Laplace transform of both sides, and so we're going to use our basic rules for the Laplace transform. So we're going to have the Laplace transform of V out dot of t plus 1 over RC times V out of t. And we're going to find, well, we have the derivative, so that's going to be the plot, and this is linear, so we can break this up and essentially do it a piece at a time. So the Laplace transform of the derivative is going to be S times V out of S minus V out of 0 minus, and then the Laplace transform of 1 over RC times V out is just going to give us plus 1 over RC times V out of S. Okay, so we collect our terms and we just have V out of S onto S plus 1 over RC and then minus our initial condition. And the Laplace transform of the right-hand side is just the Laplace transform of 1 over RC times Vi of t, and we just know that's going to be 1 over RC times Vi of S. Okay, it's going to be dependent upon what Vi of S. That's going to determine what that Laplace transform actually is. But we'll be able to work with this algebraically instead of using differential equations. Okay, so if we write everything together, we're going to have V out of S onto this expression, S plus 1 over RC, and then minus our initial condition, and that's going to equal 1 over RC times Vi of S, the right-hand side of the equation. Now, we've seen this structure before, and that was kind of the point, is we kind of go over this from several different perspectives. So you see how these things are all tied together. They're all essentially the same mathematics. It's just we kind of have different angles on them depending on how we're using them. Okay, so now we want to solve for V of S, and we're going to do that algebraically. And again, that's really the major point here, is that we've taken the differential equation and we've transformed it into something that allows us to use algebra instead of calculus to manipulate things and solve for the output. Okay, so solving for V out gives us the expression Vn of S is going to be 1 over RC divided by the quantity S plus 1 over RC, and then we deal with our initial condition, so we have V out of 0 minus times a similar fraction, but it doesn't have the 1 over RC on top. And essentially then we could convert back to the time domain by doing the inverse Laplace transform. So I'm going to say that V out of t is going to be the inverse Laplace transform of the quantity Vi of S times 1 over RC over S plus 1 over RC. All right, and then I can also say plus the inverse Laplace transform of V out of 0 minus times 1 over S plus 1 over RC. Okay, so now I got to think about what I got going on here. Well, I can't really do this inverse Laplace transform directly. I mean, even if I have values for R and C, right, I would be able to handle this part of it, but I have to first multiply this by Vi of S, and so that's going to be determined, defined, I guess, explicitly by what the input signal actually is, or the input waveform actually is. However, I can, because I know that V out of 0 minus is just a number, I can at least handle what's going to happen for the initial condition. And so I can summarize this again by saying, well, I'm going to have the same thing here. I'm going to have the Laplace transform of Vi of S onto 1 over RC over S plus 1 over RC. Again, yes, that's redundant, that's repeated, because that's exactly what we have. But then I'll highlight what we'll get for the initial condition response. So that's going to be plus V out of 0 minus times e to the minus t over RC. Okay, so this is just going to be something that's going to be a scalar times an exponentially decaying waveform. So this part we can handle directly as long as we know what that initial condition is. Okay, so we're going to look at several different scenarios for this RC low-pass filter. So this particular scenario is going to be that the input is the delta function. If you recall, the delta function is defined as just 1 for t equals 0 and 0 everywhere else. Okay, so it's also sometimes called the unit impulse. And so it's 0 everywhere except at t equals 0 where it is 1. All right, so if you recall the Laplace transform of this, the Laplace transform of delta of t is just 1. Okay, so that's really convenient because the output then, V out of t, is just going to be, if you recall, it's the inverse Laplace transform of Vi of s, right? So Vi of s in this case is just a 1. So I'll go ahead and write it here, just a 1, just so we remember it's there. And then times 1 over Rc divided by s plus 1 over Rc. Right, so that adopts the strategy we just had on the last page, and I don't have any initial conditions, so I don't have to worry about that term. Well, I can also then look at this and see, well, that's going to be just an exponential type function, so that's going to give me just 1 over RC times e to the minus t over RC. Right, so that's going to be the time domain response to this RC low-pass filter when the input is a delta or an impulse and the initial conditions are 0. Okay, so if we wanted to plot this, we would see that it is just an exponentially decaying function that has an initial value at t equals 0 of 1 over RC. So it's just going to look like that as it asymptotically heads towards 0. At least that's the best I can draw it right now. Okay, so the next thing we want to consider, again, it's the RC low pass, just like we've been using. We're going to use this for the next several examples. But now we'll have the same impulse input, so delta of t, and now we have a non-zero value for the initial condition. I'm just going to call that k volts. So essentially the capacitor has a voltage of k volts on it at t equals 0. Okay, so following the analysis that we've already done, we're going to see that, first of all, the response due to the delta is going to be the same kind of thing that we had before. It's just 1 over RC times e to the minus t over RC. And then the response due to the initial condition is going to look the same. It's just going to have a different scale factor. So we're going to see this k e to the minus t over RC. And so obviously we can combine these into 1 over RC plus k onto e to the minus t over RC. And all that's going to do is serve, the k value here is going to serve to shift the initial point on the axis up or down. And what I mean by that is now I have 1 over RC plus k. Obviously k could make it go higher, or it could bring it down depending on the value of k itself. But I'm going to have my exponential decay from whatever that combined point is. And so it just shifts it up or down. Okay, so in this next incremental example, we're going to go a little bit further. Now we're going to have that the input is the unit step function. So we've gone from something that is an impulse that is non-zero for just an instant in time to something that is going to shift from 0 volts to 1 volt at t equals 0 and then remain constant from there on out. Okay, so and then also we have 0 initial conditions for this case. Okay, the first thing I want to remember is that the Laplace transform of u of t equals 1 over s. Okay, so now that's going to modify this thing that I have to take the inverse Laplace transform of. So I'm going to have my expression for V out of t is going to be the inverse Laplace transform. And now I'm going to have this 1 over RC divided by S times S plus 1 over RC. Okay, so we've dealt with that expression a number of times. And so I can go ahead and just say, well, I'm going to use partial fraction expansion on my V of S. Okay, so right, because this is going to be my V of S expression in here. So I can say that that is going to be, so let me write that explicitly here and just say my V of S equals 1 over RC divided by the quantity S times S plus 1 over RC. And then I know I can do partial fraction expansion on that. And in doing so, I'm going to be able to write V of S as, right, it's going to be A over S plus B over S plus 1 over RC. And when I do that, I'm going to find that A is going to be 1 and B is going to be minus 1. So this is going to be 1 over S minus 1 over S plus 1 over RC. All right, just remember, we don't have to deal with initial conditions here, so I can take the inverse Laplace transform, and I can say V out of t is going to look, well, the first term is going to be 1 over S. It's just going to be a constant, right? So it's going to be 1. Now it's going to be a U of t, so it's going to be a unit step, right? It's going to look just like this does. And then, but I also have another term, so it's going to be 1 minus e to the minus t over RC. And then all of that's got to be multiplied by U of t. Okay, so if I want to plot that as a function of time, I'm going to have something that starts, because I have 0 initial condition, it's going to start at 0, and then it's going to be 1 minus this decaying exponential, so it's really going to kind of go the other way, and it's going to come up and ramp up and asymptotically go toward 1 volt. Okay, so probably no surprise there. We've talked about this form, and I'm sure you've seen this many times, but that's what's going to happen here for the unit step input to our low-pass RC filter. The major takeaway, again, I just want to re-emphasize so this becomes sort of natural to you, is we did this analysis without doing any calculus, right? We essentially, yes, we have these differential equation relationships, and we've talked through this a number of times, looked at this relationship, but this iteration, so to speak, we did this strictly using the Laplace transform, and we took advantage of the tables where needed, so that we didn't even have to do any of the calculus at all. So we solved this algebraically and arrived at a solution that we would normally have to go through calculus techniques with an integrating factor and all that kind of stuff to get this result. Okay, so we're going to go another step forward with the RC low-pass filter, and in this case we have a unit step input and we have a non-zero initial condition. Okay, we'll go directly to our output expression. In time, V out of t is equal to the inverse Laplace transform of 1 over RC divided by S onto S plus 1 over RC. And we've already worked that out. We know what that's going to look like. But now we have to handle the initial condition term. And again, we've already essentially worked that out. But I'm going to go ahead and write it in here. So that's going to be plus K e to the minus t over RC, right? It's not dependent on the input in any way. So this is the same no matter what our input is actually going to be. This term is just going to add to it if K is non-zero. All right, so I can go ahead and write what the inverse Laplace transform is going to give us, which we already know, but I'll go ahead and take care of it anyway. So I'm going to have 1 minus e to the minus t over RC, right? So that's the part that's due to the input, and then plus k e to the minus t over RC, and that's the part due to the initial condition response. And so I can combine terms to get something that looks like 1 minus the quantity 1 minus k onto e to the minus t over rc. And again, don't forget the u of t. Got to put that in there when it's all said and done. Okay, so this is going to have a similar look to it. It's just that the initial condition response, this here is going to shift the starting point of our function up or down, but it's going to always end at 1 volt because we have a unit step input. So in the long term, the steady state value is going to converge on 1 in the limit. Okay, so just so you can see something that may be a little bit interesting, we're going to look at what's going on here for several different ranges of values for k. Okay, so the first plot in the upper left, this is going to be the case where k is less than 0. The next case will be when k is between essentially 0 and 1. The next one we're going to have k identically equal to 1, and then finally k greater than 1. Okay, so in all cases, I want to have the value of 1 on my plot. Go ahead and put in my dashed line for each case. And so then when k is less than 0, I'm actually going to start down here, okay, at the value of k. Now that's going to be negative, right? And then when k is greater than 0, but less than 1, I'll start up here somewhere. When k equals 1, I will start right here, and then when k is greater than 1, I'll start up here somewhere, and I didn't leave myself a lot of room. Okay, so through the magic of editing, I was able to fix the fourth plot. So now I'm just going to quickly draw in each case what's going to happen. So when k is less than 0, again, I still have to converge on 1 volt. So I'm just going to have something that is going to rise up like this, but it's going to start from a value less than 0. When k equals 0, we've already looked at that because that was the 0 initial condition response. Okay, so when k is between 0 and 1, okay, so when k is between 0 and 1, again, I'm always going to converge like this. Okay, when k equals 1, interestingly, nothing is going to be changing. I'm just going to ride that line. I'm going to have a constant output response, and then when k is greater than 1, I'm actually going to drop exponentially from my k value, my initial value, to 1. Okay, so just something to think about. You know, this isn't terribly earth-shattering, but you know, it is interesting to think what the initial conditions can do, because most people just think of this response as something that's going to start at a quote-unquote low value and increase with an exponential shape to 1 volt. But obviously, wherever it starts with initial condition, that's going to change, in some respects, the nature of that curve. So just an interesting thing to look at. Okay, so the next situation we want to look at is, again, our RC low-pass filter, but this time the input is going to be cosine of omega t times u of t, and I'm going to have 0 initial conditions. So we've already worked the problem many times with the RC low-pass filter to responding to a cosine wave, a sinusoidal input. So you may think that this isn't anything too exotic, but the difference here is that we're starting with 0 initial conditions, and we're not presuming that we've reached sinusoidal steady state. So essentially, we haven't been operating in this sinusoidal mode for a quote-unquote infinite amount of time already. We're starting with 0 volt input that switches at t equals 0 to a cosine that then goes on forever. All right, so we're going to see that the response methodology that we have here is going to show us that the output is going to have a sinusoidal component to it, but it'll also have some sort of decay transient component. And all of that's going to come out naturally by use of the Laplace transform. So we don't have to build anything kind of kludged together. It's just going to come out naturally in the way that the Laplace transform works. Okay, since VI is a cosine, we would know that by a table, I mean, you could do the integral if you want, but VI of S is going to be S over S squared plus omega squared. Okay, so that's just the general form there. Okay, so then we know that the Laplace transform of the output, V out of S, is going to be the Laplace transform of the input, so S over S squared plus omega squared onto 1 over RC divided by S plus 1 over RC. Okay, and so that's just going to equal 1 over RCS divided by, I'm going to write it in this order, S plus 1 over RC onto S squared plus omega squared. Okay, so to simplify our writing here, I'm just going to say that I'm going to define lowercase a equal to 1 over RC. Okay, it's just going to make our writing a little cleaner, and hopefully, and then things will work out better for us. Okay, so given that, I'm going to be able to say that my V out of S can be written as capital A over S plus A, right? And then plus, I need some other, I need a first degree polynomial here, so I'm going to write it as BS plus D over S squared plus omega squared. Now, why D? Well, only because even though we're not writing it in these terms here, I don't want to confuse this coefficient here with my C that I use. So it's just a safety thing here so I don't get confused what variables I'm working with. Okay, so, and again, that's going to have to equal, I'm going to rewrite this expression here with my little a term. So that's going to have to be A of S over S plus A onto S squared plus omega squared. Okay, so to handle the partial fractions, I'm going to multiply, again, both sides of this expression by this S plus A onto S squared plus omega squared. I'm going to multiply both sides by that. So I'm going to get something that's going to look like A onto S squared plus omega squared plus BS plus D onto S plus A. And as I move that along and collect terms and do all the algebra here, I'm going to end up with something that looks like A plus B onto S squared plus AB plus D onto S, and then plus the constant term here is going to be A, capital A, omega squared plus little a times D. And then I've got to compare coefficients. So essentially solving the system of equations that I end up with. And there's a little bit of tedium involved in doing that, but it's just, you just got to persevere through it. It's really not horrible. But I'm going to end up with A can be written as negative little a over the quantity A little a squared plus omega squared. All right, and then B is going to be the negative of that. So B is going to be little a over, again, the quantity little a squared plus omega squared. And then D is going to look like omega squared divided by, again, a squared plus omega squared, and that's little a. So there's a lot of commonality in those expressions, which is good for us. Now again, all of these values here would be known from the circuit, right? Because little a is 1 over RC, so we know what R and C are, and omega is going to be the frequency of the input cosine. Okay, so all of these are defined completely. Okay, so if this means I'm careful, I can write my expression for V out of S, and I'm going to collect a bunch of terms out in front, so I'm just going to write this is going to be equal to A over A squared plus omega squared. So again, that's constant once we've established what the input frequency is going to be. And again, the A terms, the little a's represent 1 over RC. And then I'm going to multiply this by my negative 1 over S plus A. Okay, so basically if I multiply this coefficient out front times negative 1 over S plus A, I'm going to get what this expression would be. Okay, the first term in my partial fraction expansion. And then I'm going to do the same thing for the next two terms that will be split up just because of the nature of them. But I'm going to have a plus s over s squared plus omega squared. So that's going to come from the bs over s squared plus omega squared. That's where that term comes from. And then the last one is going to be plus omega over a onto the quantity omega over s squared plus omega squared. Okay, so you may think, well, that seems kind of cryptic, but it's really not that bad. It all fits together. I essentially just took these terms here, the a, b's, and c's, put them back into this expression at the top, and then really actually factored out the a over a squared plus omega squared to simplify. So I did that kind of all in one chunk there, but it's not so bad. Okay, so now all that remains is to look onto our table and see if we can find any structures that match these things. So first of all, again, once we have an input frequency, this value is a constant. This is going to look like an exponential decaying function. This is going to look like a cosine, and this is going to look like a sine that is scaled by some value here. All right, so let's go ahead and plug things in and see what we get. Okay, so looking at this, I'm going to say V out of t equals, well, I can still leave this term out in front. It might help me to do so. But I am going to go ahead and convert back I'm going to plug in the value of 1 over RC for my A. So I'm going to say that's going to look like 1 over RC divided by the quantity 1 over RC squared plus omega squared. Okay, and this is going to be on, and then just because I like to do it this way, I'm going to rearrange the order a little bit. So I'm going to start with this term just because I want to put the cosine first, but that is just the Laplace transform of cosine of omega t. So I'm going to be able to write cosine of omega t right here. And then I'm going to put the sine term. Well, again, this part here is the sine, and I have some scaling here. I have omega divided by a, and remember a is 1 over RC, so it's actually going to be omega times RC. So that's going to be plus omega RC onto sine of omega t. And then I'm going to take care of this term here, which is just going to be minus e to the minus t over RC. Okay, and then all that's got to be multiplied by u of t. All right, so this includes all features in the actual time domain response. Okay, so I'm going to have my forcing function, that's the cosine. Okay, so that's really no surprise. I'm going to have this exponential decaying term because that is going to be due to the transient portion of the response. So where does this sine term come into play? Well, if we think about that a little bit, what's going to happen to this RC filter based on the input frequency, right? If it's very low frequency, then there's not going to be much magnitude adjustment, right? The magnitude's going to be, the gain, we'll say, from a Bode perspective, is roughly 0 dB, or unity gain, and there's going to be very little phase shift. Okay, so it's going to be dominated, this cosine is going to dominate directly. But as we increase in frequency, we're going to see a reduction in the output magnitude, and we're going to see a phase shift. And it turns out, see, I don't have a phase on this cosine, nor do I have a phase on the sine. But what I do have is a weighted sum of a cosine and a sine, and that weighting not only is defined by RC, but it's also defined by omega itself, which is the input frequency. So it turns out that I can take a cosine plus something times a sine, and I can convert that to a cosine that has some non-zero phase angle. Okay, so that's essentially what would happen here, and we're not going to work that out. It's just an interesting thing to note that this is what happens. This is all built into the time domain response that we get for this filter, and we did it without using calculus. We did it by taking everything into the frequency domain using the Laplace transform, Then we rearranged and did some algebraic work to put things in a convenient form, and then we used the inverse Laplace transform to give us back the time domain signal. So hopefully you can see from this that the Laplace transform really is a powerful analysis tool. And we get more than just the sinusoidal steady state response here. We get everything that's associated with the response of this linear time invariant circuit, we'll call it. Okay, so in our next segment sort of this portion of the discussion, I'm going to talk about the fact that we can include the initial conditions directly within the circuit model or the circuit diagram, and we can incorporate them then directly into our analysis techniques, and we don't have to learn any new rules really. Everything still works the way that it did, KVL and KCL and all that kind of stuff. You just have to be careful how you build it up. So I'm going to still use the RC low pass filter. Again, it's a common example because we have a lot of familiarity with it, but yet it's a good proving ground for some of our techniques. And so before we get into that, I want to recall the voltage model for the capacitor that we had initially, right? So we have the capacitor voltage model. Okay, so this is from earlier in our discussion. And if you recall, that was VC of S is equal to 1 over SC onto I of S, and then plus the initial condition voltage divided by S, right? And then that dividing by S just had to do with when we took the Laplace transform and rearranged to solve for voltage. That S had to pop out underneath the V. I guess I should call this VC of 0 minus. All right, so now I can incorporate that directly into the circuit diagram. If we think about what our circuit diagram needs to look like, right, I have my resistor, and then I come all the way over here to my output terminal, and right here I'm going to pick off to go down to the capacitor. But now what I'm going to do is I'm going to go ahead and draw the capacitor the way I normally would, and then below this I'm going to draw a little voltage source, and that's going to deal with this term here. Right, so then I can go ahead and draw the rest of the circuit. So I'll label my resistor R. This is going to be labeled as an impedance 1 over SC, because we're going to do this in the frequency domain. This is going to be my initial condition voltage, and this is going to be VC of 0 minus over S. Right, so that's what this voltage is. Okay, I can label my input and output voltage. And again, we're in the frequency domain, so this is VI of S, and this over here is V out of S, and that equals VC of S. Okay, so that is the capacitor voltage, right? Because the capacitor connects this terminal to this terminal. But we do have just this source here just handles the fact that that capacitor may have some voltage on it as t equals 0. Okay, so once we have this, we can do analysis the same way that we always did. So if we wanted to look at a current model, right, we know that the current flowing here, right, that's going to be VI of S minus V out of S divided by R. Okay, so if I want to write what the current is, I know it's going to be I of S equals VI of S minus V out of S over R. Again, no surprise. That's the current, like I marked up here, going through the resistor. And we also know that that has to equal V out of S, right? We have this node here, V out of S, minus, now this voltage here separates us from ground, or common. So we got V out of S minus V of 0 minus over S, and then that whole thing divided by the impedance of the capacitor, which is 1 over SC. And we notice that dividing by 1 over SC is the same as multiplying by SC. So the right-hand side can actually be written as just SC onto the quantity V out of S minus V out of 0 minus divided by S. That's inside there. So that's what the right-hand side can be. And then on the left-hand side, if I want, I can go ahead and just break that up to start moving things around. So that would be VI of S over R minus V out of S divided by R. Right, so I have an equation that I can deal with. Now I'm going to rearrange and collect terms, and so that'll end up looking like V out of S onto SRC plus 1 equals VI of S, and that is plus RC times V out of 0 minus. Okay, so I can continue on, then I can divide both sides by SRC plus 1, and so I'll get V out of S equals V in of S times 1 over SRC plus 1, and then plus, I'm going to put V out in front here, V out of 0 minus times the quantity RC divided by SRC plus 1. Okay, so if I look carefully at this 1 over SRC plus 1, right, I can factor an RC out on the denominator, which means I have to put that factor in the numerator to keep everything kosher. So I'm going to end up with V out of S is going to be V in of S times 1 over RC divided by S plus 1 over RC, right? Well, we've seen that before. And then I do the same thing for this term. It's going to be V out of 0 minus onto what just becomes 1 over S plus 1 over RC, right? So the RC here got rid of the what would be a 1 over RC in the numerator. And if you go back and look, this is exactly the relationship we had earlier when we were talking about the RC filter, RC low-pass filter with non-zero initial condition. And we didn't have to specify what the input is here, right? It can be anything. And then we can get back to the time domain by taking the inverse Laplace transform. Just to point something out here, we know this one, this term here is going to turn into a decaying exponential. And this term here is going to be dependent on what VI of S is. Okay, so it really does work this way. We can build circuit models that have the initial conditions built directly in, and we can do KVL, KCL, mesh analysis, nodal analysis, whatever we like. Again, we just have to be careful when we build up the circuit model that we get everything organized properly and keep track of the algebraic signs and things like that. Okay, as the last component of this discussion, I want to talk about this relationship. We haven't really mentioned it specifically, but it is an important relationship in signals and systems analysis, and that is for the class of systems that we're dealing with, which are called linear time invariant systems. Now, the concept of linearity, I think you should be getting comfortable with. The concept of time invariance, it's important to what we're doing here, but we haven't really formally dug into it, and we're really not going to. We're going to sidestep it a little bit, but essentially what we mean by time invariant in this context is essentially the circuit parameters do not vary with time. Okay, so if I delay the input to the circuit, then the output, let's say I have a circuit that has an input Vn of t and it has an output V out of t. If I delay that input by 10 seconds, then the output will be delayed by 10 seconds. There's no real surprise there. So that's what this time invariance actually means. The linearity is probably more important in the context of what we're discussing. So if you recall, and again, back to our example of the RC low-pass filter, that if I input a delta function in, so if we want to think of it, I'm going to draw it sort of as a block diagram here. So I have delta of t, right, and that's going in to my circuit here, and I'm going to draw this just as a block, sort of a block diagram. I'll put a C on it as a label for my circuit, and then I have the output. Okay, so if I put in delta of t, I get an output that I'm going to call h of t. Okay, it's an output. I can call it y of t if I want, but I'm going to call it h of t for a specific reason. Now, if you remember, when I put in the delta, the unit impulse, then h of t, the output for my RC low-pass filter, h of t, looked something like 1 over RC e to the minus t over RC. Okay, so that was the response of the circuit to an impulse where I had no initial conditions, right? So I'll even put over here 0 IC, 0 initial condition. Okay, so what I call this is the impulse response. Again, that's not a surprise because it is the response of the circuit or the system, if we want to think of it in more generic terms. It's the response to an impulsive input. So the impulse response is the response of the circuit to an impulse input. Now, what happens if I take the Laplace transform of little h of t? Okay, so I'm going to say the Laplace transform of h of t. Well, to remember the definition, is the integral from 0 to infinity. And I don't have to worry even about my 0 minus. I'll put it there, but we're assuming 0 initial conditions. So I'm not going to have anything at 0 minus, but that's okay. So that's going to be the integral from 0 to infinity of h of t times e to the minus st dt. Okay, so carry on, then that's going to be the integral from 0 to infinity of 1 over RC times e to the minus t over RC times e to the minus st dt. I'm going to pull the constant out in front, 1 over RC, and then I've got times the integral from 0 to infinity. Now I'm going to combine the exponents here. So I'm going to have e to the minus, and I'm going to have s plus 1 over RC, okay, and then times t, and then dt. And so that's going to give me, I'm going to bring this exponent down, right? I got to divide by that when I do the integral. So I'm going to write that as 1 over RC divided by a negative s plus 1 over RC, right? And then I'm going to multiply that times e to the minus s plus 1 over RC times t, which I have to evaluate on my limits of integration. Now, we've done this a number of times, but when I do this evaluation here, when I have e to the minus infinity, essentially, then that e to the minus infinity is going to be 0, and then the lower limit of integration is going to be e to the 0, which is 1. So this thing here is going to turn into just 0 minus 1, or just negative 1. Right, so then that means the final expression here, it's just going to negate this negative here. So I'm going to get something that looks like, I'm going to call the Laplace transform of little h of t, I'm going to call that capital H of s. And that's going to be 1 over RC divided by s plus 1 over RC. And hopefully that doesn't look surprising to you, because this is the transfer function of that low-pass filter. Okay, so that's an extremely important result. Matter of fact, it's a definition, essentially, that the transfer function for a linear time-invariant system is the Laplace transform of the impulse response of that system with 0 initial conditions. Okay, so what's a major takeaway here is this thing called the transfer function of a linear time invariant, or sometimes refer to it as an LTI system, is the Laplace transform of the impulse response with 0 initial conditions. Okay, so repeat that back to yourselves several times, because this is an important facet in many areas of electrical engineering and other engineering disciplines. So it's a key result. It's something that's very important to know and understand how this works. Now, the why it works out this way is a little more involved and beyond the scope of the class, but there's a lot of good things that maybe you can look forward to learning about this whole transfer function thing. So depending on the area of electrical engineering you get into, you may deal with transfer functions on a regular basis. So understanding the concept of where they come from is pretty important. Okay, so what this really means for us, if you recall, we wrote the transfer function h of s equal to v out of s over v in of s. Okay, so what we can actually get from that is, right, if we rearrange this, we know that v out of s is going to equal to the v in of s times h of s. So if we know the transfer function for our system, and we know the input, and we can compute its Laplace transform, and we multiply those two things together, then all we have to do is compute the inverse Laplace transform of the resulting expression to get the time domain response of the system to any input. Okay, that's an extremely powerful thing that we can do. Now, it does presume, at least in this particular form here, it does presume zero initial conditions, but that's a reasonable assumption for a lot of situations. But even if we don't have zero initial conditions, we've already seen in our discussion that we have ways to deal with that. So using the transfer function is still an important thing. So we just tack on the initial conditions when they exist. And again, just be careful about the bookkeeping. So hopefully this is kind of an eye-opening result for you, and this is something that you'll run into many times over in your career as an electrical engineer, depending more or less on the branch of electrical engineering that you get into. So anyway, hope this was good for you. I appreciate you listening, and have a great day. Thank you.